Have you ever wondered what happened before time even existed? Picture a universe so tiny that everything we know was packed into a space smaller than a marble. Then, with the loudest cosmic pop you've ever imagined, no drum roll, just pure creation, that point expanded into everything we see today. Or maybe it was a cosmic hiccup. Don't worry, it's not contagious. Hello, everyone, and welcome to Big Snap Lab, where complex science gets a friendly twist. Today, we are uncovering the Big Bang Theory without heavy equations, but with clear ideas and a little humor. Grab your virtual lab coat and imagination as we rewind to the origin of space and time. Ready? Many people picture the Big Bang as an explosion of matter from a single point, like an enormous bomb going off in empty space. In truth, there was no bomb and no pre-existing space to explode into. Space itself stretched, carrying energy and matter with it. Think of the universe as raisin bread dough. As the dough rises, all the raisins move apart, but there is no central explosion. It is this expansion of space that we still observe today, over 13 billion years later, thanks to Edwin Hubble's observations of receding galaxies. In the very first instant, less than a trillionth of a trillionth of a trillionth of a second after time began, we enter the Planck era. At this scale, our known laws of physics break down. The temperature soared to more than 10, followed by 32 zeros Kelvin degrees. Imagine trying to measure something at the Planck length, a trillion times smaller than a proton. Gravity and quantum mechanics merged into a wild dance. What really happened there is still a mystery, debated by theories like string theory and loop quantum gravity. We only have mathematical clues, not direct evidence. Then inflation kicked in. In an eye blink, less than a trillionth of a second, space expanded by a factor of about 1 billion trillion. This rapid stretching solved puzzles like the horizon problem and flattened the universe like a cosmic pancake. Imagine blowing up a tiny balloon to the size of a stadium in the time it takes to blink. That dramatic growth seeded the tiny fluctuations that led to galaxies forming later. Without inflation, the universe would be too lumpy, and life might never have had a chance. As the universe cooled to around 1 billion degrees, free electrons finally started to combine with protons and form neutral hydrogen atoms. This transition is called recombination. Suddenly, photons no longer scattered off electrons and could travel freely for the first time. Those photons have been journeying across space for nearly 13.8 billion years to reach us. We detect them today as the cosmic microwave background radiation, an ancient snapshot of the young universe. In the first few minutes, protons and neutrons fused into the lightest elements in a process called primordial nucleosynthesis. Hydrogen and helium dominated, with trace amounts of deuterium and lithium. There was a bottleneck at deuterium. It formed and then quickly fused further. The exact ratios of these elements predicted by theory match what we observe in the oldest gas clouds. If conditions had been slightly different, we wouldn't have enough helium for stars or enough water for life as we know it. Roughly 380,000 years after the start, the universe cooled enough for electrons to combine with nuclei and turn transparent. That is when the cosmic microwave background, or CMB, first streamed through space. Satellites like COBE, WMAP, and Planck have mapped these faint microwaves in incredible detail. The slight temperature variations, only 1 part in 100,000, trace the seeds of all cosmic structures, giving us the oldest photograph of the universe. Over hundreds of millions of years, gravity gathered those tiny, overdense regions into the first gas clouds, which collapsed to form the earliest stars, known as population 3 stars. Those massive stars lived fast and died young, seeding space with heavier elements. Galaxies assembled into clusters and superclusters, weaving the vast cosmic web we observe today. Modern telescopes, including the James Webb Space Telescope, are now peering back to see those first galaxies forming. Today, we confirm the Big Bang model in several ways. We measure how fast galaxies recede, redshift, and we see expansion accelerating due to dark energy. Observations of supernovae and galaxy clusters reveal that mysterious force. Yet big puzzles remain. What triggered inflation? What exactly is dark matter, which outweighs normal matter by 5 to 1? And what is dark energy, the source of cosmic acceleration? Could our universe be one bubble in a vast multiverse? Researchers use particle detectors, gravitational wave observatories, and deep space probes to search for answers. In the end, we are all cosmic descendants of that first great pop. So, next time a balloon pops, remember, you come from something even more explosive. If you enjoyed our trip to the birth of everything, hit like, subscribe, and ring the bell for more science with a smile. Leave a comment on which cosmic mystery fascinates you the most. See you in the next video.